So what if you could teach an AI the actual laws of physics? I know, it sounds like something straight out of science fiction, right? But it's happening right now. And it's on the verge of solving one of the single biggest bottlenecks in all of modern engineering. Let's get into it.
Okay, just think about it for a second. When engineers are designing a new car, how do they make sure that its frame crumples in exactly the right way during a crash to keep you safe? Or how do they know a jet turbine blade can spin at these unbelievable speeds and not just shatter? It all boils down to one critical thing: prediction. If you want to innovate, you have to be able to simulate reality first. You have to virtually stress test all your materials and watch them bend and deform and even break in the computer before you ever build them in the real world. Now, for decades, this has been the secret sauce for building better stuff. But it also creates this massive, time-sucking bottleneck in the whole design process. And that brings us to the core challenge, the thing that has had engineers pulling their hair out for years: the simulation bottleneck. See, the classic way to do this is with a technique called the finite element method, or FEM for short. It's the undisputed gold standard. And the idea behind it is actually pretty brilliant. You take a super complex 3D object and you digitally slice it into millions of tiny, simple shapes. This creates what's called a mesh. Then the computer runs these hyper-accurate physics calculations on every single piece to figure out how the whole thing is going to behave. And right there, that's the big trade-off. On one hand, FEM is unbelievably accurate. I mean, think of it like a photorealistic physics engine in a video game. But on the other hand, it is painfully slow. I mean, calculating the physics for millions of tiny little pieces takes an insane amount of computing power, and it just grinds the whole design process to a halt. But this is where our story takes a really cool turn. A group of researchers asked a pretty groundbreaking question. What if? What if we could create an AI-powered shortcut that could just learn physics? Think about it like this. Instead of running that super slow physics engine every single time, what if you could train a special kind of AI by just showing it tons and tons of examples from that simulation? They use something called a graph neural network, which is just perfect for understanding complex relationships. And eventually, after seeing enough examples, the AI learns the rules so well that it can just instantly predict the outcome, skipping that entire slow calculation altogether. Okay, but that raises a huge question, right? Most AI models, they're used to simple data, like spreadsheets or pictures of cats. A complex, irregular 3D engineering mesh is a completely different animal. How in the world do you translate something like that into a language that an AI can actually understand? Well, the first stroke of genius was figuring out how to translate the physical world of that mesh into the digital world of a network. So this is what the computer starts with. It's a traditional FEM mesh of some material. And as you can see, it's kind of a jumble of interconnected shapes. It's full of all this critical information, but to a standard AI, this is just noise. It's totally unintelligible. So here's how they cracked the code. First, they take every one of those tiny cells in the mesh and they turn it into a single point, which they call a node. Then they just draw lines or edges between any two nodes that happen to be neighbors. And just like that, the chaotic mesh is transformed into a clean, structured graph that the AI can finally read. What you end up with is basically a social network for the material. Seriously, each node is like a person, and each edge is a friendship, telling the AI exactly who is connected to whom. So that complex 3D object is now represented as this elegant network of dots and lines, and it preserves all of that crucial spatial information. But okay, that solved one problem, but it created another one. These social networks for materials are absolutely massive, so the team needed a really clever way for the AI to learn efficiently without just getting completely overwhelmed. A single one of these simulations can create a network with over 100,000 nodes. 100,000! Trying to train an AI on that entire gigantic graph all at once would be, well, too slow. So their solution is brilliant. It's called subgraph training. Instead of showing the AI the entire map of the country, they just show it thousands of random little neighborhoods. The AI learns the local rules of physics in these little tiny chunks, and then it's smart enough to apply that knowledge to the entire structure. So we've got a clever way to represent the material and a clever way to train the AI on it. But the big question is, did this whole shortcut idea actually work? Well, let's just say the results are absolutely mind-blowing. Just look at this. On the left, you've got the slow gold standard simulation. On the right, you have the AI's instantaneous prediction. The patterns, the colors, those high-stress hotspots. I mean, can you even tell the difference? They're virtually identical. The AI learned the physics perfectly. And you don't just have to trust your eyes, the data proves it. The model achieved what's called an R-squared score of 0.992. Now, just for context, a score of 1.0 is a literally perfect prediction. Getting this close on data the AI has never ever seen before is, well, it's just astonishingly accurate. But here's the real knockout punch. It wasn't just accurate, it was fast. The AI made these predictions more than 150 times faster than the traditional simulation. This isn't just a little improvement. This is a revolutionary leap forward. And here's the proof in black and white. The chart shows it all. The traditional method took, on average, 330 seconds. The AI, just over 2 seconds. What used to take almost 6 minutes now happens in the blink of an eye. So what does all this mean for the future? I mean, this incredible speed and accuracy, it unlocks a concept that engineers have only dreamed about for years: the future of digital twins. This breakthrough makes the idea of a digital twin a true reality. A digital twin is a perfect, living, real-time virtual replica of a physical object. So imagine a jet engine in mid-flight, and on a computer screen somewhere, there's a digital copy that is mirroring its condition second by second. This AI allows us to simulate its complex physics in real time, something that was just completely impossible with the old, slow methods. For decades, the speed of simulation has been a hard limit on the pace of innovation. And now, that limit is being absolutely shattered. So it leaves you with a question, right? What new materials could we discover? What new designs could we invent? What incredible problems could we finally solve if our ability to test new ideas was virtually instantaneous? The future, it seems, is being built faster than ever before.